Okay, so this is chapter 10 that I'm going to be recording for you guys. Um, this chapter is focused, so we've talked about vision, and we've talked about motivation and reward as sort of systems in our brain. But of the senses, I think we've talked about motor, functioning, and we've talked about vision so far. And so this section is focusing on hearing now in the future, hearing and music, and also a little bit of language because all of this is very involved and related to each other. So similar to the way I did the motor section, if you just take a moment and think about all the things that we need hearing for, as well as all the senses that we need in order to have language. And so if we just sort of brainstorm those things, hearing with respect to hearing, the ability to speak, as we do the way we communicate typically is through speaking, and hearing is necessary for speaking. So they're very interconnected. And in order to actually speak properly, we have a range of things that we have that we don't really even think about. So our grammar, our syntax, the sounds that we use, the sounds that we can hear and understand, our voice, the emotional quality of what we're saying. All of these really relate to how we speak, the rhythm, the tone that we use. All of these are sort of intertwined in what we know to be language. And language is one form of communication. As we talked about last time, we do also use gestures as a form of communication. But largely, speaking requires these things. We also need movement to produce speech. So if our mouths or our tongues cannot move, then we cannot produce speech in the way that we should. But we also need to be understanding not only what others are saying in order to respond to them, but also what we are saying in order to be able to produce words appropriately. All right, and music is put in here because, as you'll see, music actually functions very similar to language, and this interaction between language and hearing. Rhythms that we know in music and things that we identify and emotions that we feel when we listen to music are very similar to the kinds of emotions we feel when we hear someone speak and hear the emotional tone of their voice. So let's move forward sort of from that introduction to the actual chapter. What you'll notice is that with vision, the kind of stimulus that actually produces neural responses in the brain to give you sight is light. Okay, light waves are what give us sight or vision. However, with audition or with hearing, it's sound waves that are produced. So it's not a wavelength of light, but rather the movement of atoms throughout space as a result of changing pressure that create waves of sound, and these waves of sound are what we hear. So there's the way that sound is generally measured is in cycles of a wave, and so each wave cycle is provides us with some level of it gives us insight into the intensity or density of both the molecules and the air pressure that came about across time. So these cycles repeat throughout time, all right, and this movement of these sound waves throughout time gives the property of a sound wave. So we measure sound as cycles per second. So I mentioned one of these sort of blocks here, if you look like from here to here, is a measure of one cycle, all right? So the number of cycles that we have in any given time is called frequency. Okay, and frequency is a property of a sound wave, and it's measured in hertz. All right, so and hertz would be number of cycles per second. So if I say something is 1 hertz, it's 1 cycle per second, and if it's 50 hertz, that's 50 cycles per second. All right, and what frequency gives us is a perception of pitch, how high or low the pitch of a sound is. So the lower the frequency, the lower the pitch of the sound, and the higher the frequency, the higher the pitch of the sound. Okay, that was just an example with my voice, but the lower, so it just gives you an idea. And when you hear a low frequency sound, note that these little sine waves are sort of further apart and a little bit sort of, it looks like they're moving slower, right? Slower because this is a measure of cycles per second. Higher frequency, more of these cycles are happening faster, and and again, it's because it's a cycle per second, known as hertz. Amplitude is the perceived loudness of a sound. So if a sound is high in amplitude, then it's loud, and if a sound is low in amplitude, then it's soft. All right. So be able to discriminate between low frequency and low amplitude and high frequency and high amplitude. Frequency refers to pitch, amplitude refers to sound. Amplitude is actually measured in decibels, right? So frequency is hertz, amplitude is decibels. Okay, so and the last sort of property of a sound is timbre, and timbre is the way we sort of qualify or describe a sound. So it's not so much the frequency of that sound or the amplitude of that sound. It's actually a multiple frequencies mixed together that give that sound its unique quality. It allows us to distinguish between what is that a sound of a say even at the same sort of tone, okay, even at the same note, whether a sound is, say, coming from a flute or coming from a clarinet. It fundamentally gives us a different feeling or interpretation. Is that a male voice or is that a female voice? Perhaps. And that could deal with different kinds of frequencies that are mixed together, okay? Is that someone I know versus someone I don't know? It's the quality and complexity of that sound, all right? So I'll try and give you guys more examples with respect to timbre because it is a little bit more complicated to understand if you don't have any training in music. I don't, for sure, so it was harder for me. So I've been through this. A lot of this is just repeat. It's written down for you to go through, but also take a look at the picture to help yourself visualize and keep in your mind what's actually going on with those sound waves. All right. So this is a description of frequency. Know that humans, similar to vision, where we can actually view a certain range of light frequencies, we also can only hear a range of sound frequencies. There are other animals that are far better at perceiving either the whole range of sound frequencies, like whales, dolphins, and dogs, or maybe just a subset of a sound frequency that we're unable to hear. So bats, for example, with echolocation, they can actually hear very, very high frequency sounds that we cannot hear. And therefore, when bats are passing through, it's not like we can hear the sounds that they make for echolocation because they're at such high frequency. And then, of course, you have fish that can hear much lower frequency sounds than we can. Okay, and this is the basic description of amplitude, loudness, or the loudness of a sound. So higher amplitude, louder sound, lower amplitude, lower sound. This actually here is an article on, if anyone follows I Fucking Love Science on Facebook. If you're interested in science type things, this is actually a great place to go. to sort of get up to date what's going on in the science world. And it's not just brain stuff. But this link, actually we can visit it, is one that allows us to perceive how old our ears are. The idea behind this is that as we age, unfortunately, our hearing cells don't get renewed, okay, the hair cells that are in our ears, and therefore there are certain frequencies, especially higher frequencies, that over time we're able to hear less of. If you're the kind of person that hangs out at shows and concerts all the time, and you're listening to music at a decibel that's far higher than what your ear can really handle, you will damage these hair cells at a faster rate. So if we click on this, a nice little fox here. It's a fennec fox. This is the link. You can try it out at home. I suggest that you do it with headphones, but just to get an idea of the kind of stimuli that you'll hear, we can click on this. And of course there's an advertisement because nothing works the way I want it to. Let's try this again. Okay. And it may not work. And if it doesn't, it's fine. We can move on.
That used to be me.
Okay, great.
Now, I work for Cisco.
Okay.
Get the book at asapscience.com. As we grow older, we often lose the extreme ends of our hearing spectrum. So, how many of the following sounds can you hear? How old are your ears? Okay, if you can hear 8,000 hertz, you're both alive and not hearing impaired. But let's keep raising the frequency.
All right, and so I'll stop it there, but you get an idea. They're very high frequency pitches, or high frequency tones that he's playing to test your hearing and let you know sort of the average age that you can hear at. Make sure to listen. Oops, sorry, not closed caption. If you're doing this, watch the 1080p for more accurate results in terms of quality. All right. So that's the idea there, and there's my Facebook. Let's move that away. This is actually really cool, guys. Side note. This guy got really bored of these white walls, and so he bought a bunch of Post-its and made superheroes. I thought this was pretty awesome. Here's the finished product. Okay, back to real stuff. All right, so let's go back to this. Okay, so that's a measure of loudness, amplitude. Where we hear things that are loud and actually kind of almost too loud is 100 decibels. Anything beyond that has potential to damage our hearing. I'm sure all of us have succumbed to things beyond 100 decibels. Complexity, as I mentioned, or that measure of timbre, allows us to get a different quality of a sound. Okay, what is it that makes this sound uniquely violin versus piano, even if it's the same note? And I have a video here that sort of shows you, with respect to the different frequencies, how timbre, or these this sort of complex sounds, are made up of multiple frequencies, as opposed to pure tones, which are sort of made with like a pitchfork or something like that, that only have one single frequency. So here is this video.
Okay, so this tutorial is to show you the difference between a pure versus a complex tone in frequency analysis. So first I'm going to play for you a sine wave, and I'm going to let you look at what it looks like on the EQ screen with the analyzer. Okay, so you can see that when you listen to a sine wave, it is just one frequency, and in this case, this is a 1000 hertz frequency. Now, if I go into a different instrument, such as, let me go into the pianos first, go to the piano and the Steinway, I'm going to put the analyzer on, and I'm going to play the same tone. I'm going to show my keyboard here quick. All right, so the tone that you heard was 1000 hertz, which is about a B4. It's this tone. And as you can see, this tone has several frequencies present. Specifically, 1000 hertz is the lowest of them, but then it has a bunch of other ones as well. So that's an example of...
All right, so you get an idea there. As you saw, there were multiple frequencies going through, but you did the base sort of frequency. If you look at the underlying tone of that sound, the underlying tone or the pure tone was that 1000 frequency tone. However, there are other layers to the sound, okay? And those other layers are called overtones. They're higher frequencies that actually vibrate at integer multiples of that fundamental frequency. So if it was 1000 hertz, you would have other frequency sounds at multiples of that tone, okay? I hope multiples of that starting out frequency, that pure tone or fundamental frequency. Okay, so here you have the fundamental frequency in red, and that's number 1. So this is for a clarinet. So what the waveform of a clarinet looks like is this purple image up top. But if you were to separate out each frequency, you would see that there is this fundamental frequency. That's what everything's sort of built on top of, and then you have these overtones that are multiples of this fundamental frequency. Multiples in the sense of they vibrate at sort of twice that rate or 3 times that rate and that sort of thing. All right. Okay. So what we hear as sound is really a product of our brain, similar to what we see as vision. Okay, remember we said that what are our senses in general are a creation of our brain. So there's the question: if a tree falls in a forest, does anyone hear it? And no one's there, does anyone hear it? Did it make a sound? And the answer would actually be no. The tree did not make a sound because there was no one present in order to perceive it, okay? There were just a bunch of waves, and a wave without the brain is not a sound. It makes no sound, all right? This is sort of like for example, throwing a pebble into water. Those waves are made, right? But there's no, the waves are made in the water, but there's no input into some sensory modality for us to hear that wave. It's still a wave, though, and if there was a way that we could perhaps touch that wave in water and have our touch become neural impulses, then we would actually be able to hear that wave, all right? So because it's a movement through some medium, all right? In this case, sound is a movement through air, and unless we are present to experience it, unless there's some perception of it, then it does not exist, okay? We actually have a pretty high sensitivity, but because of all the noise that exists around us, we can't hear to this sensitivity. But really, if it was completely silent and you're in a very rural area with no sort of outside sounds, we would actually be able to detect the sound of a car motor from miles away, which is pretty phenomenal, I think. But with our busy lives, there's much less to hear. Okay, so those sound waves are converted into neural activity, similar to how light waves are converted into neural activity. both language and music, or just generally sound, give us some sort of meaning and evoke emotion. If someone is listening to, say, a very angry sounding song, let's say, I don't know, whatever the emo kids listen to nowadays, the emotion there is clear, okay? The person's feeling angry, so they're listening to something that's angry, perhaps. Let's not stereotype. Language is similar. If someone's yelling at you, you perceive that emotional context of that sound, even if you didn't understand what that person was saying, okay? So what you should know is that your brain is highly lateralized in its perception of sounds, and your left temporal lobe, remember, sort of behind your ear, analyzes your speech for meaning, and your right temporal lobe analyzes musical sounds for meaning, right? So both of them, but also your right temporal lobe, when you're speaking, analyzes the sounds that you're hearing for some sort of affective component, for some sort of emotional component. Gives you the other properties of the speaker. Who is it? What do they sound like? Is it a woman? Is it a man? So it does analyze other types of meanings from the sound that it hears from speech, but to actually understand the words, it would be left temporal lobe. In neuropsychology, a test that we actually use to analyze to see whether an individual suffered, say, left temporal lobe damage versus right, sorry about that, the way we actually test that is by saying something with some sort of affective component in a way that doesn't match what the meaning of those words are. So, for example, I would say, "Oh my God, my pet died yesterday. So exciting." All right? So I would say that. And as you could tell, the tone of my voice is not saying that I'm sad about my pet dying. What would actually be appropriate to say in that context, or the affective tone my voice should have been sadness. So I should have said something like, "Oh no, my pet died yesterday." And someone would know that something's perhaps wrong. So the test actually, if I present it in that first way, okay, "Oh my God, my pet died yesterday," and the person responded with, "Oh, that's great," that means that they are able to perceive the affect in my voice. They know that it's a positive sounding thing. So their right temporal lobe would be functioning fine. But they don't hear what I'm actually saying. They don't understand that my pet passed away, and that's not an okay thing. And therefore their left temporal lobe, something may be wrong there. And vice versa. So if they understood what I said in that first case, and they said, "Oh my God, I'm so sorry," then their left temporal lobe is probably intact, but they're not really perhaps, and maybe said nothing about, they should have said, "Well, why are you excited about that? I'm so sorry that happened." If they didn't sort of worry about why I was so excited about it, then it may be that their right temporal lobe is dysfunctional. All right. So left temporal, the actual meaning of the speech; right temporal, other details, including musical sound meaning. As we talked about, language gives us communication, and music has actually been shown to help individuals regulate emotions. If we think about which context music is used in as we develop, lullabies, for example, are actually a really good example of how music regulates our emotions. So a baby's crying, and not only are you rocking that child, but you're singing a lullaby to it, which calms them down. Okay, many people, when they're upset or angry or sad, they'll listen to music to help them actually not externalize those emotions as much in a way that might be damaging or whatnot. This article here, this link, if you are interested, go ahead and look through it. But it's a study that recently came out, and let me see if I can actually click it. Okay, there we go. This study recently was published that shows that dogs actually function very similarly in how they process sound across their different hemispheres. So dogs show a left hemisphere bias for the meaning of words. So like we tell them, come or sit or stay. Those are meanings of words. They understand what that means. So the bias is in their left hemisphere, similar to us. And then the intonation or the tone of that voice, the emotion of the voice, and who that person might be, any sort of speaker-related cues are more biased to the right hemisphere. Again, very similar to humans. So that was an interesting study. It said that if you want to sort of tell your dog what to do in a demanding way, it's probably better to be saying that in their right ear, which goes to their left hemisphere, and vice versa. If you want them to understand the affective sort of feel, the emotional feel of what you're saying, you might try the left ear. So just a thought there, but research seems to work in very interesting ways. Let's get back to our presentation. So language, as we learn language throughout development, one thing to note is that when we are children, when we are infants actually, we are sensitive to all sounds. We discriminate between various sounds very well. Okay. As we grow older, we become more accustomed to the sounds within our language and the sounds that we are reinforced to hear and speak. And as a result, the rest of the sounds sort of blend together and are not as easily discriminated. This is why the older one gets, the harder it is to learn a foreign language. There are certain sounds that we either can no longer discriminate or hear, such as I think Hindi language has certain like TH sounds that an English speaker would have a difficult time hearing, and as a result have a difficult time producing those sounds as well. And so it's just a function of efficiency, really. It'd be great if we could continue to discriminate these things, but we categorize them as the same because it's not useful to us within the environment that we're in. Now, if a child does retain those abilities to hear the different sounds or discriminate, then they can better learn a new language at the young age. Okay, it's also one reason why there's sort of a critical period for language learning, and that critical period is usually between 1 to 6 years of age, sometimes even less than that in terms of the range. So somebody who's never been spoken to will have a much smaller range of sounds that they can actually hear and produce as compared to a child that has been spoken to. And there's has anyone seen the documentary of sort of this wild child that was like raised in the sort of forest on her own, or these extreme cases of trauma that you see children who are kept in very poor conditions, sort of in dark, non-sensory, non-stimulating environment. You see these kinds of deficits in language production and learning. So we talked about the properties of music, but just know that there are also differences in how we perceive loudness. And this is, even though the amplitude is the same, what might be very loud to me might not be very loud to someone else, and this could be a product of, either they're having listened to sounds at a much higher frequency and therefore, or at much louder amplitude, and therefore they can't hear the kinds of things as well, like those loud sounds as well, and so they perceive them to be less loud, and things of that nature. So we talked about pitch, and we talked about quality. All right. Sounds can have similar frequencies or similar pitch, irrespective of the sort of complexity of that sound. So you can have different different tones across a musical scale, and that corresponds to the frequency of that tone. Whereas the quality, again, is different. It's the sort of complexity of that sound throughout. So if we look at these different notes, C, E, and G, they have varying amplitudes with that fundamental note, or that first note, the lowest note. And they also have, so it's a change in pitch, not so much a change in quality, because the quality is the same in that they're all piano notes. Okay, but the pitch of that sound is different. Yeah, don't worry about this so much. Okay. Feel free to ask me questions about this if you're unclear. I know it doesn't sound like I explained it very well. These are different pitches, and as a result, different frequencies, different fundamental frequencies. They are not different in quality, okay? Not different in timbre. So I mentioned the ear actually gets these sound waves that move through air. It converts that wave energy or mechanical energy into electrochemical neural energy, and it goes through the brainstem to our auditory cortex. And here I have a video that is discussing why it is that the sounds that you hear, the voice that you hear yourself speaking, is very different to when you hear a recorded version of your voice. It's actually very interesting. We can go ahead. I'm going to go ahead and skip it for purposes of time, but go ahead and watch it. It's only a couple minutes long. It's got some interesting bits in there. All right, so here's where everything starts. All right, everything starts out in this. Actually, let me see if this picture. Interesting. Well, let's not worry about that picture. But essentially what happens is a sound wave, in this case it's a pure tone, just made by a tuning fork, goes through our ear canal. Okay, so you have your outer ear area, middle ear, and inner ear. We'll break this up even further, okay, in how we talk about it. But just know right here you have a sound wave, enters the ear canal, external ear canal, and goes towards your eardrum. So your pinna is this funnel-like bit on the outside, if you see here, that helps direct sound waves into the ear canal. And that ear canal is this little bit here. And this is where that sound wave is directed towards. And so the vibration that corresponds with the frequency of that sound will then hit your eardrum. All right? So that wave has hit your eardrum. What that does is actually activates these three, what are called ossicles. These are tiny little bones inside your ear. And they're called the hammer, anvil, and stirrup. Partly because it's just the way that they're shaped. So if you look at the stirrup, actually looks like a stirrup, the anvil looks like an anvil, and then a hammer has sort of this hammer-like function. So it hits against the anvil hits against the stirrup, and that amplifies the sound that then enters this oval window. All right, this oval window is moving towards then your inner ear. So this part here is your middle ear. So the eardrum, the hammer, anvil, stirrup, these ossicles, and that sound is amplified and hits your oval window, all right, which is this bit here. Okay, so this region is largely air-filled. There's no fluid or anything like that. And these bones vibrate in accordance with that frequency. And when it hits the oval, what was it? Where are we? Okay, the oval window, sorry. So when it hits that oval window, it actually causes another set of vibrations through now cochlear fluid. So these, your cochlea are full of fluid, and this fluid vibrates in accordance with that amplified sound because of the ossicles, and it causes what's called the basilar and tectorial membranes to bend. Okay, so these are the membranes, both on the outside and the inside here, are sort of sandwiched. Between them are these outer and inner hair cells. The outer hair cells stimulate these inner hair cells, and it's the membrane that actually bending in accordance with this frequency that causes the movement of these hair cells. These hair cells are connected directly to nerves, auditory nerves, that translate this mechanical energy into then neural energy, right? So if we want to just backtrack really quickly, sound enters brain, hits eardrum. Eardrum sets off these ossicles, which vibrate to amplify the sound, hitting your oval window, activates the basilar and tectorial membranes, which bend the hair cells, the outer and inner hair cells. The only thing that actually allows you to hear are the inner hair cells. The outer hair cells function to just send the message to them. And so without inner hair cells, even if outer hair cells exist, an individual would be functionally deaf. So they're very, very important, and we don't actually have many of them for the amount of stimulus that we can actually discriminate, which is kind of interesting. So inner hair cells are stimulated, and then you transduce or change those sound waves into neural activity. This video here is a fun little video that I will play.
Kids Health presents How the Body Works
I know this is a little childish, but bear with me. I know my voice is probably not as exciting as this is.
with Chloe and the Nerve. A skiddly bob, a boom, a lot, chaka boom boom, yeah. Woo.
Tell me where it hurts.
I'm singing, not hurting. A doo diddly dee.
I do love the drums.
I am drumming in honor of today's quest to the ear to see how we hear.
So you're playing the drum because we're going to learn how the drum in your ear helps you hear.
That was the plan, but having managed to climb up this tree,
You found that the getting down part is not so easy?
precisely.
No worries, as the ear is coming here to here.
Delightful. Before we enter, did you know that there are 3 parts to the ear?
3 parts. Sing it, Nerve.
The outer ear, the middle ear, and the inner ear. Woo-hoo-hoo.
I'm guessing that this, being on the outside, would be the outer ear.
What a clever Chloe you are. The outer ear, also known as...
Hold on 1 second, guys. Continue watching.
The pinna, or auricle, fancy word. The pinna, or outer ear, acts like a funnel, collecting sounds to channel them into the ear canal, which is also part of the outer ear.
What are we waiting for? Let's head inside the outer ear. Ooh, what's this gunk on the floor?
You mean this glorious earwax? produced by the ear canal?
Nasty earwax is more like it.
Hardly. Earwax contains chemicals to fight off infections that could hurt the skin here in the ear canal, and traps dirt to help keep it clean.
Okay, fighting infection and keeping the ear canal clean is important stuff.
Oh, yeah. Also, earwax will help us slide down the ear canal. Woo-hoo-hoo!
To the middle ear!
Where we find the eardrum. Quietly, my dear Chloe. The eardrum is a very sensitive instrument. Ah, much better. Like my bongo drum, the eardrum is a thin piece of tightly stretched skin.
Do they work the same?
Very much the same, and also different.
Such a nerd thing to say. Explain.
A musical drum makes sound when we hit it, but no one's hitting the drum in your ear. The sound waves that your outer ear collected cause it to vibrate.
Sound waves vibrate the eardrum? Got it. What happens next?
When the eardrum vibrates, it moves a set of 3 tiny bones on the other side, called ossicles.
Obstacles? That sounds like a drum beat. Obstacles, obstacles, obstacles.
The 3 ossicle bones are called the hammer, the anvil, and the stirrup.
Huh. Those bones sort of look like those things. But the sound's journey to the brain isn't over yet, is it?
Not even close. For that, we need to pop past the eardrum to the inner ear.
There are the ossicles.
And there's the cochlea. The ossicle bones connect to the cochlea. The cochlea is a small curled tube filled with liquid. The vibration of the ossicles create waves in the liquid in the cochlea.
Are those little hairs I see?
I'm so happy you asked. The cochlea is lined with tiny hairs. When the fluid in the cochlea moves, it moves the hairs and creates nerve signals that get sent to the brain. The brain understands these nerve signals as sound. So, you hear.
What?
I said, you hear.
Sorry, I can't hear you.
But because you have earplugs in your ears.
A precaution in case you started singing again.
Ho-ho!
All right, so you get the idea there. There is a bit of a childish tone to that, but I feel like it simplifies it and gives you a nice visual of what's really going on inside that ear. All right, so these are the cilia and the hair, the outer hair cells that exist, and then you have those inner hair cells that translate the information into neural energy. All right, moving past this. This you don't need to worry about too much, but just know that fast wave frequencies cause displacement of more of those hair cells around the base of the membrane, whereas slower wave frequencies or sort of softer sounds cause displacement near the apex or the tip. So if you take a look here, this is the basilar membrane. If you unroll it, because it's that kind of snail-looking thing inside your ear, if you unroll it, you see that the thick base down there is what is tuned, or the hair cells there are tuned for high-frequency sounds, and the tip of it here, the apex, is tuned for low-frequency sounds. The hair cells, again, are what are the receptors, the inner hair cells. You got about 3,500 of them, are the receptors involved in producing sort of auditory input. And then you have the 12,000 outer hair cells that actually direct the tectoral membrane to move or sort of vibrate in a way that stimulates those inner hair cells appropriately. All right, moving on. Similar to some of the other things that we've talked about, we have to produce some sort of depolarization in the cell in order to perceive, or it gives some sort of an action potential. So when the cilia move towards the tallest cilia. Basically, the movement of these hair cells continue to make these graded potentials, and over time they depolarize the cell, which causes that calcium influx and releases a neurotransmitter, and that neurotransmitter stimulates the auditory nerves. All right, and so that leads to an impulse increase. So that's movement of the cilia towards the tallest cilia. Now, if the cilia are moving towards the shortest of cilia, you get a hyperpolarization of the cell, and you have less neurotransmitter being released. And as a result, the activity of those auditory neurons goes down. So it's a nice little, again, volume control, but in this case, literally a volume control. In the sense of how those hair cells are moving. I am not going to test you on this. This is a very complicated pathway with respect to your auditory function, but it all starts in your hindbrain, and it travels through your cerebellum. I believe that's where the olivary complex would be. But it could be, yeah, so hindbrain, moving through that, then you get towards your midbrain or your inferior colliculus, and then your thalamus, which most sensory functions go through, and then to your cortex. So while I don't want you to know the individual, perhaps regions like ventral cochlear nucleus and such, I do want you to know midbrain, hindbrain, midbrain, thalamus, cerebral cortex as the path. All right, moving through. So this is also kind of interesting that your brain has dorsal and ventral pathways similar to the production of our visual perception. And so you have, with respect to the ventral pathway, goes to your primary auditory cortex, and then your dorsal pathway projects to the regions, or your secondary auditory cortex. What the primary regions are mainly responsible for, actually let me look this up really quickly because, here we go. So the primary visual cortex system, or this ventral system, is for identifying objects by their sound, and the other system, your dorsal system, is responsible for directing our movements, so sort of figuring out sound by location, in terms of like, where are we oriented, where is that sound coming from. All right, so these primary auditory cortex A1, within a structure called Heschel's gyrus, and then this is surrounded by the secondary cortical areas, or A2, secondary auditory cortex, which is right behind Heschel's gyrus. We also have, as a part of our cortex, Wernicke's area, our auditory cortex. Wernicke's is responsible, is involved in language, but it's actually because it's involved in language perception or understanding, comprehension of language, and so it's largely within the left hemisphere, and then you have more of the secondary auditory cortex here that gives you sort of more qualitative information about the sound, right? So primary auditory hears it, secondary auditory gives more information to it, to that sound. What is it? Where did it come from? And then you have Wernicke's area that processes what the actual meaning of that sound is, the comprehension of the words, perhaps, that exist. Okay. So language, as a result, is lateralized. Most of your analysis of speech is in the left hemisphere. Most of the other qualities of speech, sound, emotion, everything in the right hemisphere. Left-handed people are actually very similar to right-handers in where their language is localized. About 70% are similar, but then there's 30% that have either bilateral representation of speech in both right and left, or it's in their opposite hemisphere. So their comprehension of language would then be in their right hemisphere versus their left. So this is where individual differences come in when we study brain function. The insula is also an important region with respect to auditory. You don't really need to know this, but this is just extra information. It's highly involved in perception of not just language, but perception of taste and some level of social cognition. So if you have an injury to the insula, you're going to have issues with both language and perception of taste, oddly, which is an interesting organization that we have in the brain. So remember when we were talking about vision and motor, we talked about a topographic organization, meaning that those parts of the brain that correspond to different parts of our body are organized kind of nicely to represent our body across the cortex in a way that's efficient or allows for efficient communication. Now, the auditory cortex has a similar organization, but it's not so much in parts of our body, but in the tone, the different tones that we can hear. And so this happens at multiple levels, right? So there is at the level of the cochlea, you have base of the cochlea displaced by high frequency, high pitched sounds, apex displaced by low frequency, low pitched sounds, and what we have here is similarly in our auditory cortex. The base of that auditory cortex here is sensitive to those high frequency, high amplitude sounds, right? High frequency, high pitch. Sorry, not high amplitude. High frequency, high pitch sounds. And down here at the apex, you have low frequency, low pitch sounds being represented in the auditory process in the auditory cortex. Very low frequencies, even though we can hear them, tonotopic theory does not explain these sounds, and we don't quite know why. But cochlear implants are actually used to help individuals transduce these high and low sound waves into neural activity, which allows some deaf people to hear based on what the reason of their deafness is. If it's a cochlear issue, if it's those inner hair cells, then they will receive this cochlear implant to help them hear. And then similar to light and touch intensity or motor intensity, the greater the amplitude of that sound wave, the more firing you have of those bipolar cells in the cochlea, and as a result, there's more of a neurotransmitter release. So the intensity of the sound would be the amplitude. The higher the intensity, the higher the reaction in your neural firing and neurotransmitter release. The same thing goes for vision. The same thing goes for touch and motor function. So like the force, remember we talked about with respect to the basal ganglia, adjusting the force, the greater the weight, the greater the sort of stimulation of those neurons. Okay, all right, this actually is important slightly. You don't need to know necessarily the region, but you should know that the cells in each of our hemispheres get input from both ears. All right, so if a sound is coming from in front of you, there would be no difference between the angle that sound is coming towards each of your ears. However, in the case of this, there is extra distance that needs to be taken into account from the right versus left in order for us to know where that sound is coming from. So if there is no difference between the angle of sound perception or sort of sound waves hitting our ear, If there's no difference in that angle, then the sound is either coming from behind us or in front of us. But if there is a difference, and say the in this case, right ear is receiving, it takes longer for that time that sound to get to the right ear versus the left. The difference that's calculated would let the individual know that the sound is coming from the left and not from the right. All right, so that's how it's involved in figuring out where a sound is coming from. That's how our brain calculates that. Okay, so we talked about music and language lateralization. We talked about ventral and dorsal pathways, a little bit more information to this. The ventral pathway allows us to identify the objects. What is it that is giving us this sound, whereas the dorsal auditory stream actually integrates auditory and somatosensory information to help us control our speech function. Right. Okay. So, question here stemming from language understanding and language processing. Language is a very universal thing. It's very useful to us as human beings because it allows us to communicate efficiently about things. Gestures are also an efficient way of communicating. And we learn language very early in life, as I mentioned, and there are multiple elements that are involved, such as syntax and grammar. Different languages have common syntax and grammar, but there are also different languages that differ. There are languages that differ in their syntax and grammar, and that might be sort of more difficult for people to understand if they've learned, say, English, and they now have to understand the syntax and grammar of a completely different language. So the two areas involved in language, we've talked about Broca's area and with respect to language production. However, Wernicke's is important also because it's related to language comprehension. And stuttering is one of the things that can be affected by sort of atypicalities, possibly in Wernicke's, but in other areas as well, and possibly at different levels. So imagine if you did not hear what you were saying in real time. Imagine if what you were hearing was delayed a little bit. Has anyone ever, I mean, obviously I can't see you raising your hands, but think to yourselves of times when you've been on the phone and there's been a delay in when your voice gets to you. You tend to want to repeat what was said, or actually the opposite usually happens where your voice is continually repeated to you. There's no stop. There's like an echo or something in the phone. It really disorients us to what's going on. There's a great video, let me see if I can pull it up, that speaks to this. This is the video. I'm going to put on a bit of it just so you get an idea of how this might work. Actually, let me show you another video. This stutter device. Cause stuttering. Let's see. Creating stutter effect. Let's see if this will bring things. I think this might. Well, no, maybe not. Okay, well, I'll find the video and I'll send it to you. But until then, let's watch a little bit of this.
You have about 10 minutes to complete these character profiles, okay?
At the Our Time workshop in New York City, young people who stutter come together in a patient and understanding environment.
I am Danielle, and I am 19 years old.
My name is Claire, and I am 8 years old.
I'm Juliana, and I'm 13 years old.
My name is Philip, and I'm 15 years old.
I'm Tyler, and I am 10 years old.
What does it feel like physically when you're stuttering?
It kind of feels, like at times, like there's like no, like air, like passing, like through you, and you're, like locked.
I'm actually going to stop this. So, what many perceive to be this sort of repeating the word like a lot is actually also part of her stutter. So, stutters are not just getting stuck on a syllable of a word or a sound of a word, but also it could be someone getting stuck on the word itself. Remember that this problem could come about in multiple ways. It could be that she has there's a sort of a delay or a interference in the hearing component of her own voice. There could also be, with everything, like with attention, we have to learn or know how to, our brain has to automatically be able to disengage the movement of a certain level of information, disengage from that, and move on to the next thing. If we're unable, if the brain is stuck in a loop and unable to disengage, then there will be a repeating of that loop over and over and over again. So that's another possible cause. Other things could be motor issues, could be causing this. And so there are multiple causes, and the way that stuttering actually looks is very different.
Like your throat.
When
people who stuttered were considered feeble-minded. I mean, word went around that George VI was feeble-minded because he stuttered.
my first word,
Screenwriter David Seidler understands the humiliation Britain's King George VI felt. As a child, Seidler suffered from a severe stutter.
He was my childhood hero. That's why I grew up always thinking one day I want to write something about King George VI.
I have received
And so the British-born Seidler scripted the Oscar-nominated The King's Speech.
Here was a man who was king. He was speaking to the world. Everyone, friend or foe, was listening to every syllable he uttered, waiting for him to stutter. And if he could do that, there was hope for me.
Though Seidler seems to have overcome his impediment, he still counts himself among the 3 million Americans and 65 million worldwide who stutter. Experts define stuttering, also called stammering, as an involuntary disruption of the rhythm and flow of speech. The person knows what he or she wants to say, but just can't produce the words fluently. Boys are 3 to 4 times more likely to stutter than girls. And just as no two people have the same voice, no two people stutter in the same way.
You may not know a child is stuttering when they're just producing one word.
Christine Weber Fox and Ann Smith are the lead researchers at Purdue University's Stuttering Project.
All right, so I'm going to stop this here, but feel free to watch the whole thing. But just know that stuttering is possibly a disruption in this auditory system, but also could be a disruption in the production system. which functions with this motor cortex. All right. We have let's see here. This is essentially looking at the interaction between these two systems. So at the very basic level, if a word is spoken, it's perceived through your A1 or your primary auditory cortex. Wernicke's area has some level of, it says sound images of words, but essentially it's able to imagine what is being said. It's comprehending the word that's being heard. Now, the other thing is when you're trying to produce speech, you have a thought. That thought needs to be visualized by the Wernicke's area. Visualized, I'm saying in quotes, and that it's sort of comprehended by Wernicke's. Wernicke sends the message to Broca's, which gets your motor system ready for actually saying those words. And then this moves to the facial area of the motor cortex, the cranial nerves involved in moving your face, and then produces speech. So you can see how this problem of stuttering could come at any of these points, right? We've talked about aphasias in the past, and one of the aphasias that we have are Broca's aphasia, so person's inability to produce fluent speech. We also have Wernicke's or Wernicke's aphasia, which is an inability to understand what is being said. So the person can speak words, but those words sound like word salad, and it's because they can't keep track of what they're saying because they don't understand what they're saying, essentially. Give me just 1 second. All right. I don't want us to worry about this. Just know, we've heard Penfield's name before. He has done these electrical stimulations to the brain. Please realize that he is a key figure in both sort of mapping out the motor cortex, but also auditory cortex. All right, you don't need to worry about all of this. You do need to know about Wernicke's, and you do need to know about Broca's, as well as your auditory cortex and what that does. This experiment that was actually done by Zatorre and colleagues was a very interesting one to map out auditory processing. So positron emission, remember, detects change of blood flow as a result of how fast or what sorts of compounds are uptaken through the blood by different parts of the brain. And so he had 3 different tasks: a passive listening task where all the participants were sort of made to listen to as a sound. Then there was a listening of words, and then there was a discrimination task. And here's what happened. So just the sound produced activation in primary auditory. Listening to words to understand what the words meant was activated in Wernicke's area. So in addition to auditory, right, just primary auditory, you'd also get Wernicke's area. And then to add on to that, discriminating different speech sounds moved frontal to Broca's area. Okay, so 3 different levels of processing, 3 different areas. You have a small temporal region, larger temporal region, parietal, Wernicke's, and then you have Broca's, which is frontal, right? Remember that discriminating is more of a top-down process. I have to decide which is which, and that would be more of a frontal function, right, than just plain listening of a sound. Similarly, they did a task like this with music. Music is very similar to language. In fact, it has a language-like sort of process. So rhythm and and tone and all of these things are very similar to things that we use in language to make it melodic, to make it make sense and have meaning. And so what they did was they had someone listening to just bursts of sound. This is Heschel's gyrus in the right hemisphere. This is noise. Then if they're listening to melodies, it got processed in the right hemisphere and in the secondary auditory cortex. So this is sort of at the same level of comprehending a sound or a word, but in this case it's comprehending a melody. And then if they were to discriminate between different pitches, that would be frontal lobe activation, and that's very different. That's very similar to comparing different words or discriminating different speech sounds. Some of this might be genetic. There is a genetic influence in terms of pitch perception. People who are perfect pitch perceivers, it's very genetic. Also language is genetic. Your sort of ability to produce language, and then this idea of like knowing what note is sort of off, that's also innate. Very small children actually show errors in neural responses when they hear sounds that are not, sort of don't follow the tone or don't follow the rhythm properly. Music can also be used as therapy. It's actually been used more specifically in therapy for Parkinson's disease or stroke, disorders that have motor problems and need some sort of fluidity in their motor function. So the rhythm of that music can actually help them improve their gait and their motor function, which is pretty interesting and phenomenal. It's also been used within the context of depression, providing some level of motivation in that way. And finally, I think this is probably one of the last things that I'm going to talk about, that birds are known to sort of produce songs, and these bird songs function very similar to how we humans use language to communicate. It's very species specific. There are actually preferences in birds that have never even heard their own sort of species song, but when they're exposed to different songs by different species, they have a preference for their own species, which gives us insight into maybe it's an innate function or sensitivity. And also bird songs, very similar to language, have different dialects. Even amongst the same bird species, you have different areas and they'll have different dialects, which is kind of cool. It's the same sparrow, but depending on where in San Francisco Bay they're hanging out, one might have a surfer dude accent and the other one might have like a very, I don't know what happens on Sunset Beach, but I'm sure it's different. Okay, and I mentioned all of this. And very similar to language, bird song is actually very sensitive to a critical period. If it doesn't happen at that time, it doesn't really happen. Oh, finally, actually, echolocation. So we've talked about being able to orient ourselves to where a sound is coming from. There are animals that orient themselves visually, quote unquote, based on this very concept of sound as it bounces off of the environment around us. And so in this way, bats, for example, who engage in echolocation can tell not only how far away a target is, what the shape of that target might be, what the texture of it might be, purely based on how long it takes for those echoes to come back, the sound echoes. and they produce very high frequencies. But what's cool to know is that humans use this system, can also use this system, and more specifically humans who have visual deficits. All right, in this case, blindness. What you'll note in your book, this is Research Focus 10.2, on page 333 in the new edition of the book, the edition 4, the individuals who use echolocation to make their way around because they are blind actually activate the visual regions when it's an echo response versus if it's just a sound with no echo. So sound with no echo would activate auditory cortex, whereas if it's a sound with echo, then it's visual, because their brain has been is able to visualize now what it is that they hear and the way that they hear it. So here's a link, a video dealing with that.
At first glance, this may seem like an ordinary man out for an ordinary bike ride. But look and listen a little more closely. Daniel Kish is completely blind. In fact, he doesn't even have eyes, save for prosthetic ones. Daniel has never seen a tree, a car, or even the bicycle he's riding. So how does he know where he's going? Or how to avoid oncoming traffic? The answer can be found in the clicking sound you hear. It's called echolocation. Bats use it to fly around in the dark, and dolphins use it to navigate the oceans. Daniel uses echolocation, or sound, to see.
Every environment has its own acoustical signature. Every surface has its own acoustical signature.
Daniel was born with an aggressive form of eye cancer called retinal blastoma. By the time he was 13 months old, both of his eyes were removed.
You're 45. So you lost your sight at such a young age. You don't have any memory of vision.
I have no memories at all. I was using echolocation from the age of 2 or younger, but I really didn't know that much about it.
It was just how you adapted to your environment without really understanding it?
Yes, I doubt very seriously that most sighted people give much thought or attention about how they see. So I really didn't give much thought or attention about how I see.
Daniel uses echolocation to ride his bike, cook.
Is this a dish that you normally cook, Daniel,
No,
or are you
no.
experimenting
This is
with me?
This is a total experiment.
And even hike alone in the mountains. Using sound to see can be a hard concept for a sighted person to understand. But Daniel will tell you he sees his environment as a series of images created in his mind based on what he hears using echolocation.
So you're calling out into the environment. You're essentially asking the environment, what are you and where are you? And you're receiving those answers.
So you're getting an image in your mind.
Yes, I definitely get three-dimensional images with depth and character and richness. And I can process those, and I can interact with those.
From his modest bungalow in Long Beach, Daniel runs a small nonprofit called World Access for the Blind. Since being established in 2000, World Access has been the lone voice preaching echolocation. In fact, every major blind organization in America does not support Daniel's mission.
So, Daniel, the National Federation of the Blind will say that echolocation is just too complicated for most blind people to grasp.
It's not so much the Federation that's concerned. You have here a blindness profession, the blindness field, who, by and large, really kind of intractably remains committed, if you will, to a traditional approach, which is about, in my opinion, restriction. It is about, this is how you do things. This is the right way for a blind person to do things. This is safe. This isn't safe.
All right. You guys saw there's actually a video there. about a blind painter who's actually able to paint images, but they are blind. So that's the end of that presentation. Go ahead and email me with any questions you have. I'm going to be working on your study guide and uploading it tomorrow. I will let you know that Chapter 6 will be on the exam, so that's drug chapter. Chapter 9, visual, I will upload the PowerPoint now. Chapter 12 on motivation and reward, not including the gustation and olfaction, so whatever is in that, I'll upload his PowerPoint and you'll see that. And then Chapter 10 on sound and music and language. And then Chapter 11, Part 1, so everything before somatosensory, and I will upload the corrected PowerPoint with all the things filled in since there was a little bit of that complication on Thursday. We'll go over any questions you guys have on Tuesday. Hopefully I'll have the study guide up tomorrow so you can ask me questions about things. If they're dealing with the vision or the motivation chapters, I'll make sure to sort of have basic answers for those questions because I didn't teach them the way they did and I don't know exactly what they taught. Make sure to be specific in your questions so that I can address them properly, okay? Thanks again, guys, for being such a good sport about, the snow day and having to make up this lecture. And as always, let me know if you have questions. I am a reasonable person, so you can bring a 4x6 note card to this exam. I know there's a lot going on, and I will be as specific as I can on the study guide with respect to what you will need to prepare for. Thanks all, and take care.